everyone, my name is Shreya, and this is my Physics 2212 Lab 3 on black holes and orbits. So the purpose of this lab was to determine the mass of a black hole based on the known mass of an orbiting star, and that's for part 1. And then for part 2, we wanted to find the initial velocity of a spaceship while orbiting a planet and a moon in a figure 8 orbit. So to provide some introduction, we need to know Newton's second law, which basically tells us that the net interaction between a system and its surroundings, so the net force, is related to the object's observed momentum. We need to know the momentum principle, which basically describes that description above, and then we need to know the velocity update formula, which we can get from the momentum principle, and then the position update formula. We also need to know the gravitational force. So this basically tells us that the force felt by the system due to the mass of the source. So our R vector here is the system's position minus the source's position. We can then say that negative GMM over R squared multiplied by R hat will give us FG, and all that means is FG is related to the mass of the system, mass of the source, and then how far away the system is from the source. So to give a preview of our results, we found that the mass of the black hole is 1.05 times 10 to the 34th for part 1, and then we found out that this was the initial velocity for part 2. And then the initial conditions are listed below here. So for part 1, the system was a star, surroundings were the black hole. And then for part 2, the system is the moon, surroundings are this planet and spaceship for the first part of the calculation. And then the second part of the calculation, we switched it around and we made the system, the spaceship, and the surroundings the planet and the moon. So to provide some details on the experiment, we used Newton's second law, and then we found the universal gravitation acting on the star to derive the mass of the black hole. So basically, we just used the values we were given, which was the mass of the star, and then we derived the mass of the black hole based on FG. And then for part 2, we solved for FG net on the moon, when the moon was a system, and then we did the same thing for when the spaceship was a system, and then we applied Newton's second law and the position update formula to make the objects in our simulation move. And then based on that simulation, we used trial and error to find an initial velocity of the spaceship. So here is the glow script code for part 1. So you can see here that I edited the delta t to match the time interval, and then I calculated the initial and final momentum, the change in velocity, the change in momentum, and then dp dt, which is our change in momentum over change in time, which was the same as f net. We then found dp dt parallel, and then dp dt perpendicular, and then finally we applied our universal gravitation formula, which is listed right here. We just moved some variables around and then solved for MBH, which is basically the mass of the black hole. And then for part 2, we did something a little bit similar, but it definitely was different. So what we did was we found the gravitational force acting on the moon total. So that would include the gravitational force by the planet and then the gravitational force by the spaceship. And then we found the respective R vectors for each of these, and then found the net force acting on the moon. We did something identical for the spaceship, except we considered the forces acting on the spaceship to be the force acting on the spaceship by the moon and then by the planet. And then we found the R vectors and then found the net force acting on the spaceship. And then using Newton's second law and the position update formula down here, we were able to make the objects in the simulation move around and then kind of see what that motion would look like. So to give our results, so for part 1, with the derivation I mentioned before, we were able to find the mass of the black hole to be 1.05 times 10 to the 34 kilograms. And then this is a picture of what the orbit looked like. And then for the second part, although we weren't able to generate a perfect figure 8 here, I was able to make the spaceship loop around the moon and the planet without crashing into the moon. And then we found the initial velocity to be 2.5 times 10 to the fourth, 2.5 times 10 to the fourth, and then 0. So some sources of error here was that we approximated the initial velocity in part 2 by trial and error and just by like visually looking at the model. I think this could have probably been done by an algorithm in a more sophisticated situation. And then another source of error is that we weren't able to create a perfect figure 8 shape here. But again, this probably could have been more accurately done. And then to provide some conclusions, for the what does it mean? Basically, what's the difference between rate of change of momentum and net force? So while rate of change in momentum and net force mathematically are technically the same thing, rate of change of momentum only requires us to measure the changes in velocity of a system over time. So we just need to know the change in velocity and then the change in time, and we also need to know the mass of the object. So experimentally, this would be a lot easier to measure. First is net force. Net force requires us to find the sum of all the external forces acting on the system, which would be a lot harder to measure experimentally. And for the what if we imagined the system, we wanted system to include the black hole, star, planet, and moon, and we want to find the motion of the entire system. I would think that the dominant interactions would occur from the objects with the largest masses and between the objects that are the most close to each other. So, and then if you wanted to predict the motion of the entire system, you would also have to consider if there are any other large objects that could be exerting a net force on this system, that we just haven't taken into account. And that's it.